Hello, and welcome back. Today we will be picking up where we left off in the last video, which is exporting and importing the binary database. Before that, I would like to mention that the leaks in the last video were taken care of. The Scratchpad allocator is now up and running, and as you can see here is just a simple loop. It goes through the parse, build, and export process multiple times, and if you look over here at process memory, there is no leaking going on. So with that out of the way, let's go ahead and take a look at building the binary database. So the build function takes two parameters, the database builder itself and the file object that is parsed from the GEX file. Before we can create the binary database, we first need to prime the builder with all the parsed information. In practice, this would actually be done after all DDL types have been parsed, but in this case, we just have the one file object. We begin building by partitioning all the top-level structures which are of interest to the runtime application. Here we are separating geometry objects from geometry nodes from materials. Once all the top-level structures have been partitioned, we begin to create the database table entries, starting with either geometry objects or the materials. The geometry node table must be built last as it has references to the object and material build tables, and this would be true for any data type later on that requires references to other build tables as well. Now let's look at the process of creating table entries, starting with geometry objects. Similar to the DDL/GEX parsing, we will be following a paradigm so that changes or additions to the table creation process can be relatively painless in the future. To start, we will want to create a new object that will store the table data. Starting with the primary key, this will always be the table build types dot next table index variable. The key terminology here is fairly similar to that of relational databases. We use a primary key for the main table entry, and then foreign keys that link to other tables of interest. There are also unique keys, which are just extra table information that is not primary nor foreign, and there are also composite keys. However, these will come into play later and are a diversion from typical composite keys. Once the object has been created and the ID has been assigned, then it is safe to map the table entry ID to the name of its structure. After this, we begin adding the substructure data to the table entry, and specifically here we go from geometry objects to mesh. And one thing I would like to mention about this that I forgot, the mapped key entries, or the mapped entry keys, will be used later for the reference building. So stepping into the mesh now, we see the similar paradigm boilerplate, create the entry, assign the entry ID, map the entry, and then loop through substructures. However, the mesh has something a little special going on, and this will be clear a little more later, but the meshes themselves do not actually have a requirement on the type of data they must have. The only requirement they have is that they must be able to be exported as vertices, vertices and normals, normals and UVs, etc. Because of this, during the table build process, the mesh, when detecting a vertex array, must use the buffer index to determine what type of vertex data this buffer is, and use that to place it into the appropriate table vertex array entry. And just as a reminder, the buffer index is generated from the GEX file during the parse process. So just how DDL primitives signal the end of a build chain, there are certain MDB structures that cannot have any further table entries to build. Here, vertex arrays are an example of this. Since there are no more table entries to be built, we still create the table entry, assign an ID, and map it. However, we just now simply copy the relevant table information to the table entry. After this copy occurs, we end this function and recursion ends, and we simply trickle back up to the next build chain. Now, very quickly, I'm going to show the index array build as well. It's essentially just the same thing as the vertex array, but instead of using floats, we use U32s. Now, hopping out of geometry objects and into the materials, you see the same exact structure. But when it comes to moving from parsed information to binary, the distinction between a color and a texture specifically for materials no longer exists here, as we see just the texture build table being used. Now, a texture is any storage of graphic data. In our case, the GEX color passed from the file is an example of a diffuse texture, as this texture will only describe surface color of the object it gets applied to. So now, similar to vertex and index arrays, a texture entry represents a stopping point. As previously stated, a texture may be either a GEX color or a GEX texture. However, in this case, the MDB texture will be created from a GEX color. Due to the nature of texture data, a 64-bit number is split into two parts, a bow and a ward, and these are the composite keys I referenced earlier. Doing this split allows the number of color channels and the texture size to be encoded into the same object. In this case, the keyword is bits 0 through 60, giving a size of up to 2 to the power of 60 or 1 exabyte worth of graphics data. And the key bow is the bits 61 to 63, giving up to 4 present color channels. Setting the key bow and keyboard is simply a matter of manipulating bit offsets with the desired size values. Another composite key is also used, though, to encode texture width and texture height. This time, the 64-byte number is split essentially evenly into a high and low 32-byte number. But just like vertex and index arrays, since this is a stopping point, at the end, we copy the table data into the entry and move on to the next thing. Before moving on, I do realize that this composite business may be a little confusing. Here is the entire overview of how it's working. So it's simply just bit manipulation using kind of a pivot point as to where on this particular composite key the information changes. The one thing I do want to point out is this composite mask. It's just essentially a copy of a key not present, which is just a flag for 64 max, so it's just all ones in binary. But this is used to determine, well, specifically when specific key data is not present, and we just reuse that here as the composite mask. So now with the material and object tables being built, we can finish off with the geometry node table. And the geometry node table simply links the information from the materials and the geometry objects into actual instanced object nodes. Building the substructures is straightforward. The transform is very simple, just copy the table data from the parse structure. The material and object references don't store the data directly, but rather they store the primary key referencing the table entry holding the data. And this is what I was talking about earlier, where the mapped key entries will be used for references. One thing I can note for change in the future is there will need to be better support for objects with multiple references. I do not believe the parser is actually able to do that properly at the moment. However, luckily, each substructure of the geometry nodes are all stopping points. So at this point, the database builder is all set, and we can now move on to actually exporting the binary database. So to start, I would like to show the format in which the binary data will be laid out. Each binary table will have a table header and a table payload. The table header stores the number of table entries as well as the amount of bytes required to store all the table entries as well as their payloads. The table payload is a collection of table entries, and each of these have a similar pattern where they also begin with a header and a payload. The entry header is made up of all primary, foreign, unique, and composite keys that are required for the entry, and the payload is used only by entries which have some sort of variable data like textures and vertex arrays. Not all table entry types will have active use of their payload members. The actual binary database creation process is a series of table conversions and then table exports. Binary table conversion is a templated function that takes the database builder table that we will be converting into the binary table, as well as all database builder tables that hold substructures which need to be placed also into the binary reference. The function begins by creating enough room for the entries of the data type, and then these entries are populated in a loop over every present entry in the database builder table. The actual conversion process is done inside convertMDB, which is an overloaded function that takes the database builder entry, the relevant database builder tables for substructures, and the binary database entry that is being populated with the converted data. Each convertMDB function is responsible for converting the database builder data into the binary file format, which this was the binary file format. Each of these convert functions will return with a function call to entry size, which is just a addition of the size of the binary type as well as any dynamic storage required for that specific entry's payload. The return size is continually added to the binary table header payload size, and then once each entry has been converted, we return and repeat the process for every binary table we wish to create. Now, I won't be going over each convertMDB function as they're fairly straightforward, but I will show you where it is in the code so you can find it on GitHub if you wish. So if you go to the main project on GitHub, you can find the MDBs in persistence, MDB, and then the binary, and then binary types. And this contains each of the convertMDB functions. Although I will talk about this one here for the meshes because I said I would earlier. So there's not too much to be said here other than we convert each vertex array independently and add the active flag for that array to the header. This is a very specific case. Most of the conversions are fairly simple, but just due to the nature of what type of mesh data you might have, this is why we split it up like this, so that we can determine if there was a key, just exactly what there is for each mesh. And then this will be used at runtime to determine, okay, we have normals, UVs, vertices, but we don't have tangents or bitangents, things like that. And then at the end, these are all temporary, by the way. Once all these temporary ones are built up, then we actually create the meshes payload and then populate the payload with the appropriate data, should it be present. So once we have finished converting each of the database builder tables into binary tables, we can go ahead and begin the export process of those binary tables. This is, again, a templated function, but this time there are no overloaded functions we are invoking. So the steps are as follow. Simply write the table header to the database, followed by looping over every entry in the binary tables and writing the record. The entry record is written using this process. First, write the header, then a null pointer that will be used on load to point to the payload data, and then write the payload data itself. By doing this, it allows each table to be loaded directly into memory, following a single pass over each entry to send its pointer location. This greatly increases the locality of the imported databases. So I believe this was already kind of shown earlier with the demonstration about memory allocation, but now I'm going to go ahead and show the exporting of the two GEX files into respective MDBs. First starting with the test.1 or test1, and then now with test2. Now, I mean, it's of course binary data, but one quick thing we can eyeball here is if we look in, we had a few key not presents that were written. And reading the file, we know that key not presents were straight ones in binary, which were Fs. And that's exactly what we get here. I believe this would probably be the materials. And then down here, these are the geometry objects themselves. Now, last but not least for today is importing the binary database. The import process is actually very straightforward, with the biggest thing being to remember you need to import in the same order that you exported in. And actually you can see here I left myself a comment about doing just that very thing. So to begin the import process, we first create a binary table object that will be a result, and we write the table header information to it. After this, the payload size is read from the header, and the table entries allocates enough memory to store each binary entry. After the memory is allocated, the table entries are read and a loop begins over every table entry to align the payload pointer to the payload itself. This technically does create undefined behavior when there are no payloads, but object with no payloads should never have a payload access, so use with caution. Once the loop is complete, the binary database is returned for use. And now, similar to the export process, I will show the import and the resulting information. This is the import of the first MDB. So we have just our one object, our one material, well, texture, and then our one node. And then now we will import the second one. And here we can see much more was imported. Now, in all fairness, a lot of the mesh data is the same since it is just the same cube that was copied over and over. But I did do my best to try and change up the world space data just so you could know for sure that there's no funny business going on with he's just reprinting the same objects. One thing I want to talk about is the allocator used for the import. The database builder and exporter are very free and well to use the Scratchpad allocator since those are actions that will all be taken in an offline environment, so it doesn't really matter how long Scratchpads are held and all that. We can live with that. But during runtime, however, the database import should be moved to a more permanent allocation scheme so that the Scratchpad doesn't need to be held arbitrarily long. I would also like to talk about what can be expected next. This video took some time because I wanted to have a pretty clear idea of how the runtime use of these binary databases would be. Originally, I thought the entire binary would be loaded into a single runtime database, however, this appears to not be the right choice. The runtime database itself will still provide a good and proper solution to much of the data, but only if it's shared. For example, an inventory type system would more than likely experience worse performance if it was to be placed into a shared runtime database. For this reason, the MDB files will still be a single file format used as an intermediary for runtime data, but there would be many invocations of what could be considered runtime databases. And these databases will all be specifically designed for the set or single type of data that they are handling. But that should just be about everything needed to be said for now. Thank you for your time, and I hope you have a good day. I will see you next time with some runtime databases.